Today on How It's Made. Plastic cups and cutlery, a key ingredient for disposable dining. Special effects makeup, the behind-the-scenes secrets. Gold, mining their own business. And harps, we pulled some strings to bring you this report. The industry calls it single-usage plasticware, but that's just a fancy way to say throwaway plastic dishes. Plastic plates, bowls, drinkware, and cutlery come in many styles and colors. So for your next party, you can go disposable for everything from champagne flutes to parfait glasses. Factories make cutlery by injecting plastic into molds. They make cups, plates, and bowls using a different process called thermoforming. Before the forming phase can begin, an automated system loads polystyrene pellets into a machine called an extruder, adding pigments for colored plastic. The extruder heats the pellets until they melt, then forces the molten plastic through a die to shape a hard plastic sheet about 2 millimeters thick. They use molds to form this continuous sheet into plastic cups. First, the sheet passes through a 3-meter-long oven that heats the hard plastic until it becomes malleable. Then it enters the thermoforming machine, which simultaneously pushes and vacuums the sheet into the mold cavities, forming row after row of cups. The entire process takes just 3 seconds. The cups then travel to the trimmer, which uses a die to cut them off the sheet. The machine grinds up the leftover plastic and remelts it into new sheets, so there's no loss of material whatsoever. The trimmer feeds the cups directly to a machine that stacks them, then feeds them to a conveyor belt in one long line. The conveyor transports them to a machine called the lip roller, which reheats the cups just enough to make the plastic flexible. Then, as we see here in slow motion, it folds the rim over, forming a rounded lip. They also make cutlery from melted polystyrene pellets, as well as from polypropylene, a lighter, more flexible, and less expensive type of plastic. The cutlery molds consist of 2 halves. You can see the difference in this fork mold. In one half, the utensil cavities are right side up, the fork prongs indented. In the other half, the cavities are upside down, the fork prongs raised. A plastic injection machine melts the pellets and injects the molten plastic into the mold. A built-in cooling system solidifies the form in about 10 seconds. The extracted cutlery drops to a conveyor belt that leads directly to the automated packaging equipment. For certain customers, such as fast food restaurants, the factory packages utensils individually. The automated wrapping machine cuts polyethylene film to size, heat sealing the ends. This factory also uses polypropylene pellets to make straws. The black beads are pigments to color the plastic. An extruder, a different one this time, melts the pellets, then forces the molten plastic through a circle-shaped die. As the long, continuous straw exits the extruder, it cools and hardens in a tank of chilled water. As it leaves the tank, a knife chops it into individual straws. They fall onto a conveyor belt, which transports them to the packaging line. Just like the forks, these straws will also be individually wrapped, but in paper, not plastic film. The wrapper machine feeds them one by one into a paper sleeve. Gears mesh the edges together, creating a crimped seal. The dies on this machine turn ordinary straws into flexible ones by forming a corrugated section that lets you bend the top of the straw toward your mouth. The machine compresses the corrugation to preserve the shape. Back to the plastic cups now. This factory can print customized designs in up to 6 colors applied simultaneously. Ultraviolet lamps built right into the printing press dry the ink instantly. Polystyrene is naturally transparent, but combining 2 grades of polystyrene creates plasticware that's semi-opaque and also highly flexible. On How It's Made, we usually stick to the show's title and show you how products are manufactured. But this next segment is about special effects makeup, the kind that makeup artists use on theater and movie actors. So in this case, we'll show you how it's made, but we'll also show you how it's applied. Watch as this special effects makeup artist works his magic to transform this 28-year-old woman into a senior citizen. After gelling her hair flat, he glues on a bald cap using a theatrical adhesive called spirit gum. He protects her eyebrows and eyelashes with petroleum jelly, then covers her face in alginate, a material for taking dental impressions. Then he applies wet plaster bandages. After 25 minutes, the materials harden into a mask. Now he lines it with plaster. In a half hour, the plaster hardens into a perfect replica of the woman's face. Like putting non-stick spray on a baking pan, he coats the model in a release agent. Then, using professional-grade plasticine, he begins to sculpt an elderly face. He smooths out the wrinkles with strong rubbing alcohol so they'll look realistic. He uses a bumpy rubber pad to give the skin an aged orange peel texture. The finished sculpture sits in water for 2 to 3 hours. This activates the release agent, detaching the plasticine from the plaster underneath. Now the artist carefully cuts the sculpture into sections. The number of pieces varies with the size and complexity of the mask. Now he can finally start producing the mold he'll use to cast the old lady face mask. First, he takes a thin plaster impression of each piece. Then he coats the impression in plaster to make the positive half of the mold. Once it hardens, he applies the plasticine piece to space the depth of the mold cavity. Then he coats that in plaster to create the negative half of the mold. When that hardens, he applies release agent to both mold cavities, pours in hot gelatin, then closes the mold. In a half hour, the gelatin hardens into a flexible replica of that particular piece of the plasticine sculpture. He then implants synthetic hairs to create eyebrows. Now, using surgical glue, he begins to apply the pieces, called prosthetics. He starts with the largest face piece first. It includes the nose, cheeks, neck, and upper lip. He cuts a hole in the chin area so that he can apply the chin piece. Now, the lower lip. He cuts off the excess, then glues the edges of the chin piece to the large face piece. Now for the forehead. Again, he applies glue along the edges to connect it to the rest. To age the eyes, he uses contact lenses. They create a ring around the iris, a typical feature of elderly eyes. Using tweezers, he applies eye bags, again gluing the edges to the rest of the mask. And finally, some wrinkly eyelids. With the mask fully assembled, it's makeup time. Using a toothbrush, the artist sprays it unevenly over the mask, then smudges it with his fingers. This technique creates a realistic look because the human face, aged skin especially, has color variations. Using a very thin brush, he accentuates some wrinkles by creating depth with a darker color. Now, some freckles and age spots. And a gray wig. And finally, just a bit of lip color because lips dull with age. All this takes an experienced makeup artist about a month of work, and such expertise doesn't come cheap. A major transformation like this for stage or screen can cost up to $10,000. Gold is the softest and most malleable metal. It can be pressed extremely thin, crafted into various shapes, even drawn out to form a fine wire, and all without breaking. Gold isn't affected by water or oxygen as many metals are, so it doesn't rust or tarnish either. Most gold comes from lode deposits, also called vein deposits, concentrations of gold and other metals in the cracks of rocks. Lode deposits require hard rock mining, the process of removing gold-bearing rock, called ore, by drilling and blasting. Miners descend more than half a kilometer underground. There, they drill holes for explosives using what's called a long-hole air drill. They drill in a specific pattern set out in a plan prepared by the mine's engineers. The engineers know exactly where those veins of gold are, thanks to the mining company's geologists who've studied ore samples. The company collects these samples by drilling deep into the rock at 15-meter intervals. These diamond drill cores, as they're called, are up to 100 meters long and measure 3.5 centimeters in diameter. Gold in its natural state isn't pure. It's usually intertwined with silver and other metals, so the mined ore has to be processed afterward to isolate and extract the gold. A metric ton of ore yields only about 6.5 grams of gold. After blasting the rock apart with explosives, miners use what's called a muck machine to transfer the ore to cars headed to the main shaft and then above ground to the mill. There, a crusher reduces the large chunks into smaller rocks about the size of road gravel. A mill then pulverizes them to the texture of beach sand. The factory adds a water and cyanide solution, then another mill grinds it further into a mud-like pulp. The pulp flows into large settling tanks. The wet solids, being heavier, sink to the bottom. The water at the top drains to another area. They transfer the wet solids to an agitation tank and blow in air. The oxygen sets off a chemical reaction between the cyanide and the gold trapped in the ore, triggering the gold to dissolve and leach into the surrounding water. Drum filters then separate the water from the solids. This water now joins the water that was separated earlier. They pour in zinc powder to solidify the dissolved gold and form pieces containing both zinc and gold. To smelt it into bars, they first have to mix several chemicals: manganese dioxide, fluorite, silica flour, borax, and sodium nitrate. This chemical mix, called flux, will separate the gold from the impurities. They pour it into the smelter, whose temperature is a fiery 1600 degrees Celsius. They rotate the smelter so that the contents heat evenly. Over 2.5 hours, the heavier gold eventually sinks to the bottom, while the impurities, called slag, float to the surface. They pour out the slag, taking a sample to make sure it contains no gold. If it does, it goes back in until it's gold-free. By now, the gold has cooled slightly, so they reheat to 1600 degrees Celsius, then cast into bar-shaped molds. The gold takes about 4 minutes to solidify, then another hour to cool completely in a basin of cold water. They extract the gold bars from the molds and clean off any slag residue. gold bars are also called ingots. At this stage, the gold is 80% pure. The Royal Canadian Mint will refine it to 99.9%, the international gold standard. Harps come in many sizes. The type that classical musicians play is known as the orchestral or concert harp. It produces more tones than any other stringed instrument. The player plucks the harp with the thumb and first 3 fingers of each hand, while at the same time operating foot pedals. The harp is one of the oldest string instruments, originating in the Middle East as early as 3000 BC. Harps began appearing in Europe in the 700s. They initially had a curved pillar. By about 1500, this evolved into a sturdier straight pillar that could support more tension. As music became more sophisticated, they added a second row of strings, as well as pitch-raising mechanisms, enabling the orchestral harp to produce more notes. This harp is a cross between a classical harp and a Celtic harp. There's the pillar in the front, the sound box in the back, and the neck running across the top. The sides of the sound box are called the ribs. They're made from 7mm thick pieces of solid poplar. The instrument maker traces a rib-shaped template on the wood, then cuts out the shape using a bandsaw. He clamps them onto his work table, then, with a plane, makes them symmetrical. Now he draws 3 lines across each rib to mark where he'll cut slots. You'll see what those slots are for later on. Next, he glues on a notched strip of wood called a lining to the curved side of the rib. The lining enlarges the gluable surface, making it easier to assemble this side to the back of the sound box. The notches enable the lining to bend to the curved shape. Now he glues on the lining that will connect the straight side of the rib to the front of the sound box. He shaves off some wood with a small plane, then rounds off a corner. He planes the back lining as well, removing a corner to flatten it. Trimming the linings reduces the final weight of the instrument. Now he cuts off the ends of the linings on both sides to be able to slide into place the adjoining parts, the bottom plate and the top plate. They're made of Russian plywood, which is a piece of plywood sandwiched between 3mm thick sheets of birch wood. He glues the top plate into place, then clamps it. He does the same with the bottom plate. He closes the back of the sound box with what's called the back plate. It's also cut from Russian plywood. He glues it onto the lining, applying pressure with tight rubber strapping. When the glue dries about an hour later and the strapping comes off, he marks the location of the sound holes, the holes from which sound exits the instrument. He constructs the top plate on the front of the sound box from solid spruce. He lays the pieces down from widest to narrowest, then glues on a reinforcement strip made of solid maple. The strings pass through this strip and another on the inside. They prevent the tension from rupturing the top plate. He attaches a solid poplar frame to strengthen where the top plate and ribs join. After sanding with fine sandpaper, he coats the sound box in varnish. Remember those slots in the ribs? They now hold bracings to prevent the ribs from bowing under the tension of the strings. Using a bandsaw now, the instrument maker cuts the neck from a 2-centimeter thick board of Russian plywood. He makes a slot for gluing the pillar, also made of Russian plywood. Once the varnish on the neck and pillar are dry, he hammers in pins for the strings. This type of harp has 34 strings. Brass bridge pins space them evenly apart. Steel zither pins adjust their tension for tuning. He uses a wooden guide to hammer the pins to a uniform depth. The 3 finished pieces fit together with dowels and slots. He secures the joints with glue and a long screw through the pillar. Strength is critical. This harp has to withstand 360 kilos of string tension. Reaching through the sound holes, he threads the strings through the reinforcement strips to the pins outside. These are nylon strings. Harps can also have steel strings. He winds them around the zither pins with a special key. The last step is to tune the harp with the help of an electronic tuner. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net. The How It's Made crew vehicle is courtesy of Subaru Canada.